there it is. All right. So I'm going to be cherry picking on easy topics that you already know from your undergraduate studies, but I'm going to cherry pick them in order of significance. So what I want to do is I want to cover today a little bit about Fourier series expansions and how they relate to solving partial differential equations. All right, so we need to do something about partial differential equations. And I am not going to go to any significant depth, so I may disappoint you, some that are looking for fancy things, because this is an elementary class, so nothing is fancy. And there is another math course. So there is another class in engineering mathematics that covers only partial differential equations offered in the spring, but only a very small percentage of you most probably will take it. Most of you say, this class is enough, right? We got tired already. Okay, so we're going to cover, not today, but I'm going to introduce today this concept of boundary value problems, which is a departure from initial value problems. I'm going to tell you what the difference is. Then in preparation for solving boundary value problems, I'm going to introduce Fourier series. On Wednesday, I am going to tell you a little bit about separation of variables for solving some of the fundamental PDEs. And the three fundamental PDEs of interest to our lectures are the heat conduction equation, the wave equation, and the Laplace equation. Okay, and I'm trying to, actually I gave you, I think, one of each in the homework set. Certainly not enough, but we will, so maybe amend the homework with some additional problems. All right, so we need to discuss about boundary value problems. I remind you, all the problems we have done up to now are initial value problems, right? We have time as the independent variable. Maybe if it's a second order initial value problem, we provide the initial displacement and velocity, and then we try to solve this thing forward. So today we're going to discuss boundary value problems. So we are actually, in the lecture today, there's not going to be any time dependence. And we will see the difference from the initial value problems. And I'm interested in partial differential equations, which means that instead of having one independent variable that was the time t in the earlier lectures, now we're going to have x and y and z, all right? So we're going to have more than one independent variables. So the idea here is we're going to be able to come up with some easy way to solve these problems using a technique that's called separation of variables. So we're going to write the solution as the product of solutions that depend only on one variable at a time. And this is going to lead to ordinary differential equations, which is what we know. And the actual solution of the PDE is going to be some linear combination of solutions we obtain from ordinary differential equations. Okay, so we're going to naturally come up with Fourier series approximations or sine and cosine approximations of the solution of PDEs, but instead of sine and cosines, and we will certainly see this next week, we may have an expansion on Legendre functions or Bessel functions. And we will see the type of functions we get are extremely tied to the differential equation we're solving. In the same way that eigenfunctions are tied to a matrix A. So actually, we're going to generalize this idea of eigenvalues and eigenfunctions today. Okay, and that's for our introduction. So we're going to move away from this equation. This is what we have done up to now. We had an initial value problem with some initial displacement and some initial velocity. And now what I'm going to do is I am going to have a problem where let's say the variable, the independent variable is location x, okay? So still, the equation looks similar to this, but notice I have two boundary conditions. So if you think of a road, right? One end is at x equal a, another end is at x equal to b. I'm going to provide the solutions of the differential equation at those two ends. These are my boundary conditions. Now you may say, well, it doesn't look any different from this. You know, these are initial conditions. These are boundary conditions. Well, we will see that the solutions to these problems are extremely different, day and night. All right? So this is an initial value problem, and this is a boundary value problem, and particularly is what we call a two-point boundary value problem because we provide the solution at 2 points. These two boundary conditions that you see here, they are not the most general, right? We will see many other types of boundary conditions, but I'm going to start with simple things of defining y at the two ends, A and B. All right, so you remember, you know, the definition of homogeneous and non-homogeneous differential equations. We have exactly the same thing for boundary value problems. So here is the definition of so if this is the general non-homogeneous problem, so you notice there is a right-hand side forcing term, and the boundary conditions are non-zero. So the homogeneous problem is solving this. 0 right-hand side, 0 y at the left, 0 y on the right. So that's the homogeneous problem. And so you may, I don't have room to philosophize here, right? But the homogeneous, the relation between the homogeneous and non-homogeneous problem for this boundary value problem, it's really not the same as what we have seen for initial value problems, all right? As a matter of fact, the solution, the relation between the homogeneous and non-homogeneous problem that we have to deal for boundary value problems is the same as solving the homogeneous AX equal to 0 problem and the non-homogeneous AX equal to B problem in linear equations. And you will see the relation. I'm going to do some examples today to see the relation for boundary value problems in linear algebra that we have seen in the past. Now, before we try to motivate and see some examples, let me just say that for initial value problems, if we have some simple assumptions on P and Q, for any initial conditions, we can guarantee the existence and uniqueness of solutions of initial value problems. For boundary value problems, things are getting murky. We may have no solution. We may have one solution. We may have infinite solutions. Even though, let's say, the functions P and Q are the same. And what exactly we have doesn't only depend on the differential equation, but depends very much on the boundary conditions that we're using. So we will see these through examples today. So I mentioned the relation with linear equations. So let me, since I'm going to do 2 examples, actually 4 examples related with each other, let me just remind you the relation between the homogeneous and non-homogeneous problem when we solve AX equal to B. So this is my non-homogeneous problem, all right? And the homogeneous problem is this one, AX equal to 0. So when you solve the homogeneous problem, you remember, if A is an invertible matrix, I'm taking a square matrix here. So A is n by n, okay? So if A is invertible, the only solution to AX equals 0 is X equal to 0, right? Now, if A is a singular matrix, there are infinite solutions to AX equals 0, right? We spent lectures on that topic. So if A is singular, there are infinite solutions to that problem. Now, for those 2 cases of A being non-singular and A being singular, let's look now in the non-homogeneous problem. So if A is non-singular, AX equal to B has a unique solution. And if A is singular, AX equal to B may have no solution at all if B is not in the column space of A, or it may have infinite solutions. So actually, this relation that you see here between the homogeneous problem AX equals 0 and the non-homogeneous AX equal to B would be exactly the same for boundary value problems. All right, exactly the same relation for boundary value problems. So effectively, we will know if the homogeneous problem has only the solution x equal to 0, then there is a unique solution to the boundary value problem. If the homogeneous problem has multiple solutions, then we will see that the boundary value problem, the non-homogeneous boundary value problem, may have infinite solutions. So let me do a problem, a simple boundary value problem, so we can make some sense. Nothing new. When you see the differential equation, you already know the solution, so nothing new. But it would be a boundary value problem, not an initial value problem. So is this a homogeneous problem? Right? You can see I have two ends, x equal to 0 and x equal to pi, and the boundary conditions is, I'm sorry, who said yes? This is not a homogeneous problem. Why it's not a homogeneous? I just realized it. I look at something as like, why is 0 equal to 1? So that's my real problem, okay? So that's a non-homogeneous problem, the way we introduce it. So we want to solve this boundary value problem, and we will, in one or two slides, we will do the homogeneous problem to see the relation between the two. But right now, this is what we want to solve. Now, can you tell me, looking at the differential equation, what type of solutions we have here? Just at the differential equation. We have done this infinite times. What solutions do we get? Sines and cosines, thank you. So we're going to have cosine of square root of 2 of x and sine the square root of 2 of x. And now we're going to apply the boundary conditions, right, to see what type of solutions we get. So it says y at 0 equal to 1. So if you put 0 here, this disappears. Y at 0, this becomes equal to 1. So C1 equal to 1. We agree? All right, so C1 equal to 1. How about if you apply y at pi equal to 0? What do you get? If you plug it in, right, and because of the square root of 2, there would be no cancellations here. So then you can solve that C2 is, all right, C1 is equal to 1, so this is equal to 1. So cosine of this divided by sine with a minus sign will give you C2. So this problem has a unique solution, which is given by this nice formula. Okay? So that's our first boundary value problem. Nothing fancy, all right? It has a unique solution. Okay, let's do this problem now. Again, it's a non-homogeneous problem. And one of my boundary conditions, I put y of pi equal to a, where for now a is arbitrary. You can give me any number. I'm going to use an arbitrary thing. So what type of solutions I have here from the differential equation? Again, what do we get? Sines and cosines, so we get something like that. There is no square root of 2 now. This is significant now, actually, because removing that 2 may make a huge difference. So we do get sines and cosines, but that square root of 2 is missing, so I get cosine of x and sine of x. So if you put y at 0 equal to 1, so this at 0 disappears, and so we have C1 equal to 1. And what do you get at y of pi equal to a? Y of pi equal to a? What is sine of pi? And what is cosine of pi? How much? Minus 1, so we get C1 equal to minus a. So actually, you are telling me, by applying the boundary conditions, you got C1 equal to 1, and at the same time, you got C1 equal to minus a. That's not good. that can only make sense if A is equal to -1, okay? So in general, for any A, there is no solution to this problem. All right, so it looks to me very similar to what we had before, but it has no solution in general, okay? Now, if it happens that A is equal to -1, all right? And, you know, I can take, so if A equal -1, C1 is equal to 1, and C2 can be anything. So how many solutions I have? I have infinite solutions. So this problem either has no solutions or has infinite solutions. So the previous problem that was looking more or less the same problem had one solution. Now we have either no solution or we have infinite solutions. So let's look at the homogeneous problems corresponding to these two examples to see if we can see this analog that we mentioned for AX equal to B. So let's look at the homogeneous problem. Where's my... All right, so does this problem looks the homogeneous problem of example 1? It does, right? So you remember that there was something there on the boundary condition. We remove it, and now we have y of 0 equal to 0. So let's solve this problem, all right? So this is the solution exactly as before. Apply now the boundary conditions at x equals 0. This becomes 0. This becomes 1, so C1 equal to 0. And then at y at p equal to 0, what do I get? So if you put y at p at pi equal to 0, the only way you can satisfy this is if C2 equal to 0, okay? Because C1 is equal to 0, so C2 has to be equal to 0. So the only solution to the homogeneous problem is y equal to 0. So can you see now if the homogeneous problem has only the 0 solution, then the non-homogeneous problem has a unique solution. Exactly the way we solved AX equal B. I mean, of course, I only did one example, right? I'm not proving anything, but you need to trust that somehow there is a relation there, and the fact that the homogeneous problem has only the 0 solution implies the non-homogeneous problem has a unique solution. Now, if we take the other example that we did, so this is the homogeneous problem of the second example. Again, the solution is sines and cosines, all right? And if you apply at x equals 0, this is 0, so this C1 will be equal to 0. And then at x equal to pi, what is sine of pi? 0. So basically, C2 is arbitrary. There is nothing you can say about C2. So this homogeneous problem has actually infinite solutions of the form y equals some constant times sine of x. So again, we see here the relation that I mentioned. If the homogeneous problem has infinite solutions, then the boundary value problem has infinite solutions. Or I can design a problem where maybe it has no solution at all, but we only get those cases when the homogeneous boundary value problem has infinite solutions. All right. So let me now use your imagination, and I'm not sure if you have seen this in your undergraduate studies. You remember both problems that I did, they involved y double prime plus, one problem was plus 2y equal to 0, and the other problem was plus y equal to 0. You remember that? So now how about if I put plus lambda y equal to 0, where lambda, all right, where lambda is some parameter, all right, some parameter. Now, from the results that we computed before, can you tell me for what lambdas, just from the two examples only, for what lambdas this problem has non-zero solutions? Tell me what is going on for different lambdas. One case was lambda equal to 2. So what did we conclude for lambda equal to 2? The first example we did, what was the situation for lambda equal to 2? There is a unique solution, okay. And for lambda equal to 1, what did we have? By the way, this is the homogeneous problem. I am looking here at the homogeneous problem, all right? So, so let me ask the question again, because this is the homogeneous problem. So for lambda equal to 2, what was the solution to the homogeneous problem? Y equals 0. That's the trivial solution, not of interest, okay? For lambda equal to 1, what was the solution to the homogeneous problem? I don't remember, remind me. What did we get? You have your notes in front of you. What did we get for lambda equal to 1 for the homogeneous problem? Sine of x. All right. So you know what I want you to do is now I want you to think of the eigenvalue problem. You remember the eigenvalue problem? Ax equal to lambda x. When you look at the eigenvalue problem, you're really not interested for eigenvectors x equal to 0, right? So if we interpret this homogeneous boundary value problem as an eigenvalue problem, can you tell me what are the eigenvalues based on the two examples that we did? For which lambdas does this problem have a non-zero solution? Lambda equal to? For which lambdas, we did two examples, for which lambdas this has a non-zero solution? You just told me. Lambda equal to 1. And what was the non-zero solution? It was sine of x. So effectively, this problem has eigenvalues and eigenvectors. All right, so it has characteristic solutions that they are basically not just similar, they are in line with this concept of eigenvalues and eigenvectors. So one of the things we will be interested in is to identify these eigenvalues and eigenvectors for boundary value problems. So you can think of this, and we will see this through examples. There are specific modes of the solution of this homogeneous problem, and these modes are eigenvectors. And then the actual solution to the non-homogeneous problem is really a linear combination of the eigenvectors. Okay? Need to show all of these things. All right, so there is a relation with eigenvalues and eigenvectors, right? So in this particular case, we computed, based on the two examples, that lambda equal to 1 is an eigenvalue, and the sine of x that you told me is the corresponding eigenvector. So you know what I'm going to do is, let me just actually now, since we motivated this with these examples, literally try to find out all the eigenvalues of this problem and all the eigenvectors. Is only lambda equal to 1, you think, and sine of x, the eigenvalue and eigenvector on this, or there are many more? What do you think? How about sine of 2x? If I put a sine of 2x, will it do it? If you put sine of 2x, what do you get, you think? What lambda should be for sine of 2x? Lambda would be 4, all right? Everybody looks at that? Okay, so let's see, why is that coming, from where is that coming? So we're going to see if we have eigenvalues that are negative, equal to 0, we don't really care about this, and positive, okay, because we don't know anything yet. So we're going to take that lambda is positive, so we're going to introduce, to make it look positive, we're going to take lambda to be mu squared, mu to be specified, right? So that way, the positive constraint is automatically satisfied, so we're going to put lambda equal to mu squared. And what's the solution to this problem? Can you tell me? Would be sines and cosines of what? Of mu what? Mu x. Correct? We agree? So apply the two boundary conditions and tell me what do I get out of this. If you put y at 0 equal to 0, you agree that this term is 0. Cosine of mu 0 becomes 1. So C1 is equal to 0, has disappeared. Now, we need to satisfy y at pi equal to 0. So sine of mu pi has to be equal to 0. When is sine of mu pi equal to 0? What does mu pi need to be? Sounds good. So how about if mu is an integer, all right, 1, 2, 3, then this boundary condition is taken care of. So mu equal n, so mu is equal 1, 2, 3, 4, 5, etc. And you remember lambda is mu squared. So what are our eigenvalues on this problem? Would be 1, 4, 9, etc. And what are the corresponding eigenvectors? Will be sine of nx. Okay? So here is the final result. All right? So we got basically, these are the eigenvalues. Nice. And these are now the eigenvectors. Sine of x, sine of 2x, etc. So immediately you can see, right, this relation with eigenvalues and eigenvectors. These functions that we get are characteristic functions of the differential equation. So the same way, when you compute the eigenvectors of a matrix A, here you compute the eigenvectors of the differential equation. Okay? I mean, if you actually think, even in an abstract way, at the end of the day, right, differential equations and matrices, they're all related. If you discretize one, you get the other, all right? So not surprising, but this, we work in continuum space, okay? These are the eigenfunctions, and these are the eigenvalues. And, okay, so you can get rid of these constants. You don't really care. So you can say that the eigenfunctions are what you see here. Now, I am not going to do the cases. You remember we said, okay, we will take lambda to be positive, and then you can take lambda equal to 0, and then lambda equal to negative. Let me just say nothing interesting happens if lambda equal to 0 and lambda is negative. Okay? It's in the notes. Nothing, you're not going to get anything. So basically, in this problem, lambda has to be positive to get these nice eigenvalues and eigenvectors. So I have the case lambda equal to 0, right? So this is the only thing we care. All right. So, so what we're going to actually do in the next few lectures after I discuss some fundamentals of Fourier series will be somehow to be able to identify these eigenfunctions of these homogeneous problems corresponding to our boundary value problems and somehow use those to represent the solution. But you can appreciate from this problem, the solution to a general problem will be sort of some combination of the signs, and that's a Fourier expansion, right? It will be some combination of the signs, and that will give you a Fourier expansion. But I want you to remember that when I mean a Fourier expansion here, I don't mean really an expansion that has sines or cosines, has whatever functions you get by solving this eigenvalue problem, and we will see, and you will do this in the homework, some of these functions may be very famous functions, way more complicated than sines and cosines. So it may be the Bessel functions, Legendre functions, and other weird things. Okay? All right. By the way, you can generalize this problem because before, intentionally, to make it easy, I took the ends of the domain to be 0 and pi. So you can actually make this 0 and L. And I'm just going to give you the results. You can actually verify them quite easily. The eigenvalues in that problem will be n squared pi squared over L squared. and the eigenfunctions would be sine of n pi x over L. Okay? So nothing different, exactly the same forms. The only difference here is that from that boundary condition, the sine of mu L has to be n times pi, right? So the sine of mu L has to be equal to 0, so mu L has to be n pi, okay? And that leads to lambda equal mu squared, which gives you this, and then basically you have sine of mu x, all right? So you have sine of n pi x over L. So remember this n pi x over L, because when I introduce the Fourier series next, I am going to use an expansion that has sines and cosines that have this form sine of n pi x divided by L. But I want you to remember, we don't necessarily expand in sines and cosines. It just happened in this problem that the sines and cosines were the eigenfunctions of this problem, okay? Were the eigenfunctions. So obviously, will be the easiest starting point to discuss solutions of PDEs using the Fourier expansions. Okay, Fourier series. I'm assuming you heard about them before, right? So I am not telling you things out of reality, and there is I'm going to be very elementary basically on what we need to do. So we're going to use this expansion in Fourier series to solve PDEs, but obviously, expansion in Fourier series, you don't need to use them only for PDEs, right? Somebody may, if you have an acoustic wave, it tells you what are the modes of that wave, and a Fourier expansion gives you the mode of a wave. All right, if you have a wave, in shallow waters, for example, you may ask what are the modes of this water waves. So Fourier expansions have their own reason to be around, and I was actually planning to do a lecture or two on this fast Fourier transform when we discussed linear algebra, but I realized we had no time for that. It was going to be a little bit more complicated than what we would like for this course. But if I have time when we finish some of the critical topics, I may come back and tell you a little bit about the Fourier transform at the end of the semester. All right, so what's a Fourier expansion? Let me just write it down. All right, you don't have to read anything. So you can see here it's an expansion that involves cosines and sines. And I wrote them again with the same argument that I had in the previous problem, okay? There is a constant term, and there is a series, right? There is an infinite summation over all of these terms. And the idea here is that this expansion converges to some function f. And the natural thing is to solve the inverse problem. If somebody gives you that function f, how can you compute these coefficients am and bm, all right, and a0, okay? And obviously, if you represent a function with this series expansion, the obvious question you may ask is, yeah, does this converge? Does this have the same continuity properties as the original function f of x, okay? Not sure we will answer all of this, but you can guess the answer to some of the problems that we will deal with. So, so the first thing I need to do is I need to discuss, because the sines and cosines are periodic with period 2 pi, right? So we can only do all of these things for periodic functions. So you may ask, what's a periodic function? And this is the common sense definition. A function with a period of capital T is periodic when fx plus t equals f of x. And you can see here this particular function has a period of capital T. Okay? If you have two periodic functions, like before we had the sine and cosine with periods 2 pi, obviously if you take a combination of them, the combination of them also will have a period of 2 pi. So in general, if f and g have periods t, the linear combination of this will also be periodic with period t. And obviously, I don't have to tell you this, right? We take the period to be the smallest, basically, value of t where this equation is satisfied. Because somebody will say, oh, I'm going to take 2t or 3t. So we take the smallest interval in x where the function repeats itself. So in the case of the sines and cosines, can you look at it carefully and tell me that the period is 2L over m? I mean, remember the sine. Let's say if you look at the cosine, right, it starts from 1, okay, with positive values. And then it goes to negative values and comes back to 1. So how much the argument changes in one period? If you have a cosine, what's the period of cosine? What's the period of cosine? How much? 2 pi. So if you put m pi x over L equal to 2 pi, all right? So what do you get? You get x. You get that the period, basically looking at x, is 2L divided by m. Can you see that? All right. So just remember, when I play with that expansion that I had on these sines and cosines, the period is 2L over m. So obviously, for m equal to 1, the period is 2L, and the interval that the function actually is going to vary would be the applications, and the plots I'm going to give you will be from minus L to L, okay? But the period then, in that case, would be 2L. All right. Now, why sines and cosines? So first, let me remind you the orthogonality. Again, this is a generalization of a concept we learned in linear algebra. So we define now, if we have two functions, u and v, defined in an interval a to b, we define the inner product of the two functions to be this integral. I mean, for vectors, we had u transpose v. Now, if you make u to be infinite, right, and v to be infinite, you have infinite components, don't you think that u transpose v becomes an integral? Right, just the common sense. So the inner product between u and v, and we denote it like this, is this integral, okay? And obviously, two functions are going to be called orthogonal when this integral equal to 0. Now, you need to, you will see this maybe next week on Monday, that we will generalize this definition of orthogonality to make it very specific to the differential equation we're solving. And in that case, it may come up that there is some weight, in addition to uv, you may have some other term inside that integral, okay? But right now, it's an arbitrary definition of what an inner product is, right? It has to satisfy certain properties that we discussed them during linear algebra, and you can go and verify that this thing takes care of everything, okay? So two functions are orthogonal when this inner product is equal to 0. Now, why sines and cosines? Why? Because, you know what, they're orthogonal. They form an orthogonal family. So if you take the inner product of this cosine with that cosine, it comes out to be equal to 0 unless m equal to n. I mean, it's amazing, right? All of these terms are dropped out unless m is equal to n. And if m is equal to n, if you are good in computing integrals, this integral comes to be equal to L, right? Similarly, if you take the product of two sines, is 0 for unless m equal to n. And if you take any combination of any product of a cosine with a sine, all right, then you actually get 0 for all m's and n's. I mean, how better this can get? All right? This is very nice. How do you prove this? You compute the integrals, all right? You go back to your former life as a freshman doing calculations of integrals, and you verify those. So, if let's say I give you a function f of x, and your objective is to write it in a Fourier expansion of sines and cosines, so we need to find a way to compute a0, am, and bm, and the way to do this is to use the orthogonality condition. So what I have done is I take this expansion, I multiplied left and right hand side with cosine of n pi x over L. I multiply this term, I multiply this, and multiply that. And tell me from all of these terms, what is cancelled out? Which terms are going to cancel out? How about, let's start with the easy term here. If you multiply cosine and sine and integrate, what happens? 0. If you multiply cosine with cosine, what happens? Everything drops except the coefficient, since I multiply by n, except the term m equal to n. So the whole summation there becomes an. All right? And how about this term? What is the integral of cosine from minus L to L? So remember, the cosine starts from value 1, positive, then becomes negative, then it's negative and again positive. When you integrate the cosine, what do you get? 0. So effectively, what's the answer? The answer is that the coefficient an is this integral, all right, divided by L. So if you multiply with the cosine n pi x over L and integrate and divide by L, that's the coefficient an. And I can give you all the answers, all right? Where are all the answers? So these are all the answers. And I actually put even the case n equal to 0 together because for n equal to 0, this is 1, all right? So the integral of f of x over L will give you the average of f. So that's an. And so these are the formulas that go with the name Euler formulas, okay, for the Fourier series expansion. So given an f, you're given a function f, okay, you can actually write it in a Fourier series expansion in this form. Now here we are assuming sort of that the function f is periodic, right? That's why we are able to expand it in sines and cosines. Okay? But if you have a function f that is defined from minus L to L, and you don't really care past that interval, you know what? You make it periodic, and then you expand it in Fourier series expansion, and you only use the Fourier series expansion from minus L to L. Right? You don't have to say, I need to have a function from minus infinity to infinity that's periodic. Who cares, right? If the function is defined from minus L to L, you repeat the function on intervals of 2L, and there's a Fourier series expansion. OK. So let me do rapidly a simple expansion, example. So in this case, the period you can see is 4, right? You go from this peak to that peak is 4. So the distance L is equal to 2. And we have this triangular wave, okay, looking like this. I mean, depends how you see, upside down or not. So you have this triangular wave, and we want to find the coefficients AM and BM. Can you tell me actually, before we do any calculations, are we going to have in the expansion both AM and BM or only one of those, and why? Without doing any calculations. You remember in AM, we multiply to get things with cosines, right? We integrate f with cosines to get the coefficient AM. And in BM, we multiply the function f with sines. Can you tell me if we're going to have both coefficients? What type of function is this function f, looking at this? Even. Even Steven, as they say. So if you integrate f, if it's an even function, you integrate with sines, what do you get over the period? 0. So which of the coefficients, the two coefficients, are going to drop out? Bm is the integral, you remember it's 1 over L of the integral of f sine of m pi x over L. So f is even, sine is odd, so the product is, anyways, is odd, so the integral of an odd function is, over the period is 0. So you don't, you know, if you go and spend half an hour to actually compute these things, I will not be very happy, okay, because you'll be wasting your time. So the coefficients B are equal to 0, all of them, and AM is this nice thing when m is equal to, it's an odd number, otherwise is 0. And if you put all of this together, you get this wonderful Fourier series expansion of that triangular wave that looks like 1 minus 8 pi squared times all of these nice things. And actually, this is a wonderful Fourier series expansion because of you have this term in the denominator that is 1 over 2n minus 1 squared. And why is that good? Why I'm happy to see 1 over n squared on the denominator? What is the implication here if you have 1 over n squared? It will converge very fast. So basically, right, you're going to have in a computer program to use partial sums. You're not going to sum this to infinity if you use this expansion. You're going to use n equal 2, 3, 4, 5, whatever is needed. And because you have 1 over n squared, it actually decays rapidly and it converges very fast. And I think somewhere in the slides, when it talks about convergence, it shows you plots of the rapid convergence of that series. OK, another example. Let's take this nice function. Can you tell me what's the period of this function? Without looking at the nodes, can you tell me what's the period of this function? And what is L? So what's the period of this function? 6. All right, so we have a period of 6, L equal to 3, so we have to compute the coefficients AN and BN. Let me just say something in case I forget about it on the lecture today. Obviously, this function f of x has discontinuity at -1 and 1. And in principle, because to compute the Fourier expansion coefficients, you have to integrate, even if there is discontinuity, that discontinuity does not contribute to the values of the coefficients AN and BN. Right? If you integrate something that has a singularity, and this singularity is not infinite, it's not a delta function, the integral is 0. So in principle, you don't really have to define what this function is going to be at -1 and 1. You can just leave it unspecified. However, and it's in the notes again, we will come back to it, when you write the Fourier series expansion, you do the calculation of the coefficients, the Fourier series expansions converges to a function, and that function will give you specific values at -1 and 1. And you know what those specific values are going to be for this problem? So if you go and evaluate the Fourier series expansion at x equal 1, you know what value is going to give you? 1/2. So it will give you the average, basically, of the values on the left and the right. OK? But you don't have to specify in the beginning what function f is. OK? But at the end, when you have an expansion, it converges to the average. So if you do the Fourier series expansion for this, come on, you can compute, obviously in this case, you're going to have to compute AN and well, actually, BN is again, I see here 0, right? You can see this is an even-Steven function. So it converges, and where is the expansion? And this is the nice expansion, OK? All right? So again, this converges everywhere except at the edges to the original value f of x. And at the point of discontinuity gives you the values 1/2. OK? So, so now I think we talk a little bit about the speed of convergence. This is in the first example that we did. We had 1 over 2n minus 1 squared. But look at this, actually, by the way. Where was it? Does this converge faster, you think, or what do you think? Or slower? Here, we don't have a square. We have 1 over n. So this actually converges way slower. OK, you would need way many terms. OK? So now, just to show you the two examples to see the convergence, on the first example with the triangular wave, even if you use only 2 terms in the Fourier expansion, even if you use 2 terms, look how good actually the results look like. I mean, 2 modes only are sufficient to actually capture this nearly perfectly, except obviously at the corners, okay? So that's where the maximum error is, at the corners, okay? So if you actually want to control the error to be smaller than a certain amount everywhere, you really need to concentrate one of these corners and make it equal or less to that amount, and then you can, with confidence, know that the error everywhere else is going to be way less than that, okay? So that's for the triangular wave. It converges extremely fast. I don't know if I have the results for the, so this is, you can see, by the way, the errors at, for example, at the point 0, it's huge, all right? At the point 2, again, the error is huge, but anywhere in between, this is just for 6 terms from what I can read. So if you use 6 terms in the expansion, the error is very small everywhere except at the corners. And I wanted to tell you before the time passes something, okay? So this shows you the rate of convergence with different number of terms. This is what we call partial sums. Keeping different terms in the expansion shows you how it converges. You know what? Come on. Okay. So we, you know, we talked about, said given a function f, you can find the coefficients, you can find, you know, a Fourier series expansion, but in general, when can you do this? And the only thing that you need is, you need to actually, you remember when we had functions like that? I used this before for our discussion in another lecture. Functions that in pieces look like this, how do we call them? We call them piecewise continuous, okay? So what you actually need to make a Fourier series expansion is, you need to basically have functions and derivatives that are actually piecewise continuous, and piecewise continuous means that in each interval, the function has to be continuous, and at the edges, we're allowing to jump, but those jumps have to be finite, cannot be delta functions, all right? So with only those little simple constraints, you know that there is a Fourier expansion for this type of problem, but really I wanted, because it's 11:22, I wanted to, if I can go and I'll come back, okay? I see they're coming there, okay? Give me 1 second, if I can find it. Obviously, we're gonna do this. Okay, here it is. If you try to do a Fourier series expansion for that step wave, okay, you notice that at the points of the discontinuity, you actually have these big jumps. Can you see here, right, at the points of discontinuity? It doesn't matter how many terms you're going to use, thousands, 10,000, there is nothing you can do about those points of discontinuity. And this is what is called the Gibbs phenomenon. Very important in physics, engineering, fluids, solids, everywhere, okay? So you can use as many terms as you want. That jump there in the points of discontinuity is going to stay there with you. That's the Gibbs phenomenon. So we'll come back and talk about convergence on Wednesday.